Thank you for tuning in. I'll be tackling gravitational and electrical fields. This topic's part of paper 4, paper 5 of A level physics. Very important, key topic, and forms the basis of understanding of modern physics, modern classical physics. And this topic is extremely important because it carries on till postgraduate level. But I mean, as vast as it is, I'll start off with a few conceptual misconception removals. And the first thing I'd like to do is to resolve the units of G dimensionally and carry out dimensional analysis for the gravitational constants. We'll talk about Coulomb's law, Newton's law of gravitation, and then we'll see how what's the ratio of gravitational force to electrical force and which one's more powerful. So I'll start off by dimensional analysis. Of G. So G, as we know, is part of this formula, force gravitation. G m1 m2 over distance of separation squared. And we know that masses are in kg, radii are in meters, and forces are in newton. So we have a newton and then kg squared plus meter squared. And we know from F equals ma that the actual units of force are kg meters per second squared. So if we plug that in there, we can then resolve and substitute. And that would be, we could cancel 1 kg, and that would give us kg. So we have kg here per meter squared, that's gravitation, and then we've got meters per second squared here. So we could just take it to the other side. That'll be meter cubed. So that would be m l cubed t minus 2. So this is a rather unclean, messy sort of, and so the dimensional configuration of G would be m inverse L cubed T inverse squared, and it's meter cubed per kg per second. A neat version is as such. So fields of gravitation. So gravitation fields, basically fields are, just the G fields and the E fields and the B fields. So we have GBE. B fields, they have their own formula, magnetic strength, magnetic field calculation for a wire, for a loop, for a Gaussian loop, for different kinds of, for a motor, for a generator, so on and so forth. But vast majority of comparison is done between G and E. So it's G G fields and electrical fields, gravitational fields. So this G fields are dictated and explained by Newton's law of gravitation, and electrical fields are explained by Coulomb's law, and Coulomb's law of electrostatic attraction or repulsion. So that this is what it's all about. So gravitational fields are explained by Newtonian, and electrical fields explanation, although both are inverse squared based, but the electrical fields have a lot of work done upon them by Coulomb, Ampere, Voltaire, Faraday, and all of these scientists. So history of physics is as important as the theory of it. B field, you have other scientists working on it, such as Tesla, Edison, and then you have other uncommon scientists that had their own theorems and laws in there as well. So gravitational fields, they consist of gravitational waves, gluons, gravitons, whereas electrical field consists of protons, protons, electrons, alpha particles, beta particles, beta positive, beta minus, and charged muons and charged particles, but not neutral neutrinos, antineutrinos, or neutrons, because they don't have a charge. Electrical fields are driven by charge, driven by 1 over squared, 1 over inverse of the square of distance, and so you calculate gravitational field F subscript G vector with a G constant, M1, M2. Some people write M capital and then the other one to avoid writing M1 and M2, and then this is the distance of separation squared. Sorry, not this is solar. Yeah. So and then electrical field, which is Coulombic in nature, it's calculated as K Q1 Q2 whole over R squared, distance of separation between 2 point charges. So if it's a point charge, the distance of separation would be from here to here. So K here, so this one we know that G has its own particular value, which is 6.67 times 10 to the power minus 11 per kg meter cubed per second squared. And K has a value of 1 over 4 pi epsilon, which is where epsilon is permittivity in vacuum, and it's, I think, farads per meter. Yeah, it's farads per meter. I don't remember the value, but I think it's 8.9 pico, like 10 to the power minus 12 coulombs per Newton meter. But when you put this value 8.9 picocoulomb squared plus Newton meter in here, and you solve the Euler formula, the K value comes out to be 9 billion farads per meter, I think. Hang on. Meters squared for farad? No. I think Newton meters squared plus Coulomb squared, and gets a bit tricky with the units. I should have resolved the units for it as well. So according to my estimate, it was Newton meter squared per Coulomb squared. And so rather than punching this value into here every single time, students have come up with this value that they've solved already, and that's 9 billion Newton meters squared per Coulomb squared. We've done this dimensional justification. Now we'll do it for electrical constant as well, which is we'll now find out the units of this. So we know that electrical energy would also electrostatic repulsion or attraction would also be in newtons. So if we've got a K here and we've got charge 1, charge 2, whole over r squared in the direction of r vector hat, and in the direction of r. So we know that if this is Newton and this is Coulomb and this is meters, meter squared. So then K would be newtons meter squared per Coulomb squared. Is that correct? Yeah, that is correct. And then then you can, that's pretty much it. And this is what the units of and Coulomb is Q equals, in my previous videos I did do that. So Coulomb is ampere second, and so you can do kg meters per second squared times meters squared and divided by ampere second. So that'll be, excuse me, Q is, so that would be cubed. So it's per amps, and it's they call it farad per meter as well. So these are the units of the constant. Okay. Now, if we were to figure out which ones, if we wanted to figure out which one's stronger, we'd have to do, we'd have to, we'd have to actually divide. So we'd have to equate. So if we wanted to find out which electrical or which one was more stronger amongst the electrical or the magnetic force, we'd have to actually carry out algebraic division one over the other to find out which one's more powerful. And it would be, I think, if we'll have to make it very, very uniform. So all the radii would be 1 meter. All the masses shall be 1 kg and no more. All the force would be 1 newton. Nothing more than, in order to simplify and elucidate, we'd have to do some. First of all, we'd start off with force of gravitation, and that would be G m1 m2 over r squared, and that would be 1 squared divided by 1 squared. So we would get answer as G, which is 6.667 times 10 to the power minus 11. That would be Newton meters squared per kg squared, just simply put. And then you'll do electrical energy, algebraic. Coulomb squared over r squared in the direction of r hat. You'd have, this is 1, you end up with the answer being 9 billion 9 billion newtons. 9 billion newtons. No, hang on. This would be positive here. Sorry, Newton meter squared. So meters would go over there. So Newton meter squared per kg squared. So that would be Newton's meter squared per Coulomb squared. And so now you'll have to. So one's in 9 and the other one's in 11. You'd have to divide. K or electrical energy divided by G. So you'd get 9 times 10 to the power 9 Newton. So at this point in time it's just in units, but the units will get cancelled off because both have the same sort of units, coulombs per kg. So newtons meter squared per coulomb squared, and then you'd get 6.667 times 10 to the power minus 11 newtons meter squared plus kg squared, and you'd divide it and you'd get the answer something like divided by 1.35 times 10 to the power 20. So Newton cancels, meter squared cancels, and it's squared per kg, coulomb squared per kg. There was another way of it as well. Another way would be to equate the two. G m1 m2 r squared, and then k q1 q2 over r squared, and then cancel the r squared because both of them are the same. Cancel 1 mm, and then it would come down to be the same, to be honest. And that would be and then you'd have to underroot it to get coulombs. So at the moment, we can say estimate that electrical energy, electrostatic attraction repulsion is 1.35 times 10 to the power 20 coulombs per coulomb squared per kg squared times stronger than gravitation. That's the actual ratio that comes out to be. Perhaps if we were dividing, so we need to. Now another way to actually calculate it would be to find the answers first and then divide them by each other, and then you'd get a better picture. So for this we would get the answer as 1 times 1 divided by 1 squared, and so the answer would be 6.67 times 10 to the power minus 11 newtons. And then for electrostatic we would get we would get 1111 9 newtons. So now if we take that and we divide it for if we divide this simply, we should get Okay, we would get 9 1.35 times 10 to the power 20. Orders of magnitude. Orders of magnitude. Now, please bear in mind, I did it with 1 kg worth of masses, 1 meter's worth of radius, and 1 coulomb's worth of charges, which is enormously large amounts of charge and masses. Normally, when we compare electrostatic and gravitational force together, that's between point charges, and the charges are 1.609 times 10 to the power 9 minus 19 coulombs, and the masses are electronic masses. I think it's 9.11 times 10 to the power minus 31 kg, and the radii are very, very minuscule. They are like atometer dimensions. Now you can see for that particular comparative analysis, you'd get something in the order of 10 to the 39, like 10 with 40 zeros and 39 zeros ahead of it. But if you do 1 kg and 1 meters and 1 newton's worth of it, then you'd get so we can see that by de Broglie's, if you're familiar with de Broglie, I've done a video on de Broglie in my physics playlist. So if you are familiar with that concept, then you should be able to see that the bigger the masses and the charges become, the ratio of the electrical and the gravitational force begins to decrease. But smaller the charge, smaller the mass, smaller the radii, the ratio begins to increase and become astronomically large. So that's quite interesting, isn't it?